Hello students, welcome to our today's class. Today we are on the sixth session of electricity and magnetism. And previously talking about this chapter, we started with alternating current and direct current. Along with that, we also studied about the magnetic effect of current. Along with that, we also went with electromagnetic induction, motor effect, and in our previous class, we looked at some of the sources or large sources of energy. So when we were studying about large sources of energy, we described about three sources, and we were constantly talking about how generator was connected with transformer to transmit the electric current all over the households. So today our topic is transformer, and these are our contents for today's class. Let me start you with this picture. Okay, this picture is a very simple one. You can see a phone is being charged with a charger. Now, when you look at the box of the charger at home, you will see the output is 5 volt. So it means this charger is going to deliver 5 volt to charge the battery inside your phone. Now, let's imagine a situation. Imagine that you are charging your phone, but instead of the usual 5 volt, your charger suddenly delivers 220 volt. What do you think will happen? You can think it for a while. Instead of 5 regular voltage like the regular volt that we are delivering nowadays, what if it starts delivering 220 volt? I think the very common guess was explode. And it is correct. It might overheat, it might burn and explode, and all the circuits inside that mobile phone will be permanently damaged. We cannot repair it again. Okay, so now let's again recall of our first class. When we were talking about alternating current, we said that in Nepal, in case of Nepal, the frequency of AC is 50 Hz and 220 volt. So that is the supply that we are getting in our home. The scenario right now, I was telling that this charger is delivering 5 volt. Then if you visualize, again you can see the charger is connected in the source. So it delivers 5 volt, but how does it deliver just 5 volt out of 220 volt? And what if we want more than 220 volts for our electrical appliances? How do you think it is being handled? As you already know the topic, it is being handled by transformer. These are some of the regular pictures that we see of transformers around us. We see a protective box around it, but we do not know what's inside it, right? So, let's start with a very simple definition of transformers. It is a device that modifies the voltage of an alternating current without altering its frequency. So, our motive of using transformer is to modify the voltage, but we are not going to alter any frequency. And another thing that we are not going to alter is the power. It is also used to increase or decrease voltage levels while maintaining nearly the same power. So, when we are delivering the same power, we can see that power depends on basically two factors, I and V, which are current and voltage. So, if this transformer increases voltage, obviously the current is decreasing because we have to maintain almost the same power. So, if we are using a transformer to increase the voltage, the current is going to decrease. And if we are using this transformer to decrease the voltage, the current increases. So, whatever happens in between this current and voltage, the power still stays the same. So, we are not altering frequency, we are not altering the power, we are just increasing or let's say fluctuating the voltage according to our requirement, and we use transformer for that. And as I already mentioned, it is very widely used in power transmission and distribution systems to either increase or decrease the voltage level. So in the previous slide, you saw some regular pictures that we look around us and tell that it's a transformer. Now let's learn about the actual construction of the transformer. What are the components that are present in the transformer? Okay, this is a simple core that we will use in a transformer. This is made up of soft iron, and this is not thick. They are thin plates of soft iron. And another very important characteristics that a transformer must have is laminated iron core. So these iron plates are laminated with some insulated substances. Okay, so this is one plate that I'm showing to you. This is the core of the transformer. It is made up of soft iron. It is laminated with some insulating substance. Now we use stacks of these items like this. These are numbers of plates that we are going to use, that we use in the core of the transformer. So these are the stack of soft iron core which are laminated with some insulating substances. They are stacked together. Okay, now let's look this in 2D diagram again. So now we are going to visualize this in 2D. Here we can see iron core which is laminated. Okay, now on the two sides of this laminated iron core, we can see windings of conductor like this. So these windings, or let's say this conductor, is also insulated, and they are kept a bit far from each other so that the short circuit does not happen. So we are keeping it insulated a bit further from each other in the windings of the transformer, in the windings of the iron core used in a transformer. Okay, so these two windings are connected separately. One is connected with the AC source, as you can see, and the another one is connected with the load. The part, or let's say the windings which are connected with the AC source over here, you can see the windings are connected with the AC source, right? So this part of this transformer is known as primary coil. So primary coil, it is connected with the AC source. And here you can see on the other side, it is connected with the load. So the part, or let's say the windings which are connected with the load are known as secondary coil. Okay, so now what do we know so far? We know the transformer uses iron core, soft iron core, which are laminated, and on the either sides of the transformer are the windings of the conductor, which are insulated and kept a bit further from each other so that no short circuit happens. So we also talked about the lamination of the iron core, right? So we laminate this iron core to prevent energy loss, which we will discuss in our further slides as well. Okay, so now you know about the iron core. You know which part is known as primary coil and which part is known as the secondary coil, right? The coils which are connected with the AC source are primary coils, and the coils which are connected with the load are secondary coils, and they are sometimes termed as input source and output as well. Input source is AC again, the one that is being input in this transformer, and the output source is of course connected with the load. So those are different terms, but they have this similar meaning. So we can easily identify primary coil and secondary coil. Now we know some sort of constructions of it, what type of materials are used, what are the components being used so far. Now let's talk about the principles that the transformer works on. So principle of transformers are: one is electromagnetic induction, another one is mutual induction. So about the electromagnetic induction, we have frequently talked about this in our previous classes as well. So simply, it is the process of inducing EMF in a conductor when there is a change in magnetic flux linked with that conductor. That is electromagnetic induction. And we also did a small experiment earlier in the class showing how a changing magnetic flux generates EMF in a conductor, right? So now the new term for us is mutual induction. So what exactly is mutual induction? As the term says mutual, let's see, because in the picture of the transformer we saw that only one end was connected with the AC source. So other end does not have source, but we saw there was load. So something must be transmitting the EMF towards the other side, right? So now let's see what exactly is mutual induction. So it is the phenomenon in which a varying current in one coil generates an EMF in a neighboring coil through electromagnetic induction. So basically this is a mutual work of both the coils, right? So from one coil, since the AC is supplied, what happens? The direction of the current is constantly changing. When the direction of the current is constantly changing, according to the magnetic effect of current, the magnetic field lines in the primary coil also constantly changes. So these magnetic field lines are being magnetic field lines are being cut with the conductor in the other side, not on the primary side but on the secondary coil. So secondary coil, they receive the changing magnetic flux, and with the help of electromagnetic induction we know that electromagnetic induction in case of changing magnetic flux generates EMF. So it is a mutual work for them. Let's try to visualize it more clearly. Here you can see this is an AC generator, and here you can see on the upper side you can see it is north pole, and on the lower side it is south pole. So we know AC generator. In our previous class we studied about AC generator and how it changes the direction of the current, right? So AC generator, it generates alternating current, and this alternating current also changes its path periodically. Now see, right now we can just see that the upper side is the north pole and the lower side is the south pole. So when this AC generator is constantly creating, or let's say constantly generating alternating current, this alternating current changes its path periodically. So once it completes its half cycle, the polarity also changes. As you can see, magnetic field constantly changes its polarity. Right now in this we can see that the upper side is the north pole and the lower is the south pole. But when it enters the second half cycle, this north pole becomes south pole, and this south pole becomes north pole. So this means it is changing the polarity and its intensity is also changing, right? So when this is happening, look at the other side now. Now let's take a break from this primary coil. Let's look at the secondary coil. You can see the secondary coil is connected with a load right here. It is a bulb. So these magnetic field lines, see, the motion is creating the magnetic field lines. The motion of the magnetic field lines is creating a changing magnetic flux in this secondary coil. So as we studied earlier, when a conductor is introduced with a changing magnetic flux near a magnet, it generates EMF. So we can see here AC generator is generating AC, and it keeps on changing the direction of the current, which also again changes the polarity of the magnetic field generated along with its intensity, which again changes the magnetic flux, which keeps on changing the magnetic flux on the secondary coil. And we know when the magnetic flux keeps on varying, in case of conductor, the voltage is induced. So this was the visual representation of the working of transformer. Now we will move more to the theoretical part of the construction, or let's say the structure. Okay, so now let's recall about what we studied and we will go in depth now. Now a transformer consists of several key components as mentioned. At its core there is a soft iron or silicon steel core which provides a low resistance path for the magnetic flux. So earlier we told that the laminated core was helping us to reduce the energy loss. Now it also, now another thing it does, it enhances the path for the magnetic flux. It helps the magnetic fields to easily pass from the primary coil to the secondary one. Okay, so the second point, it has already been mentioned, the current is laminated to reduce energy loss due to eddy currents. So what exactly is eddy currents? So eddy currents, okay, let me tell you that when a source is connected in the transformer, there are also circular concentric electric fields generating around the conductor. So if the generated current is in a very circular, or let's say closed loop, we call such currents as eddy currents. So we do not want that, or let's say we do not want the eddy currents to cause any energy loss in case of our transformer, because it will just decrease the efficiency of the transformer. So that is another reason that the core is laminated. Okay, so it is used to reduce energy loss due to the eddy currents. And around this core, two separate coils of insulated copper wire are wound. One is called the primary coil. The primary coil, which is connected to the input AC voltage, and the other one is called the secondary coil, which delivers the transformed output voltage. Okay, let me remind you that we use transformers in case we want to alter the required voltage. Okay, so one amount of voltage is being received by the primary coil, but the output is some other number of voltage. Now the number of turns in each coil determines whether the transformer steps up or steps down the voltage. As we can see, transformers are being used in the power stations, right, in a charger at your home as well, and they both have the similar working, but the output voltage is quite different. Okay, so all it depends. If we are using the transformer to increase the voltage, we are going to use step up transformer. If we are going to decrease the voltage by the source, we are going to use step down transformer. The details of these transformers we will study in our some other class. So the required voltage, if you need more or less, it all depends on the turns in the coils of the primary and secondary coils. Okay, so last one, to prevent short circuits, both windings are insulated using varnish or insulating materials. So I already mentioned that as well. The conductor or the coil that we use for to make turns in the coil or to make the windings, they are insulated and they are kept a bit further, so no short circuit happens during its working. So we know the construction of the transformer now. Okay, so let's try to do this one question. The primary coil creates a changing magnetic field, but the secondary coil doesn't directly touch it. Now, first question, how does the magnetic flux travel from one coil to the other? And second question, can you think of any materials that would make the transformer work better or worse? Okay, so when we studied about the construction, we were like, I was frequently telling that they are kept apart. The primary and the secondary coil are kept apart. They do not touch each other directly. So how is this magnetic flux traveling from one coil to another? Okay, let's see. The magnetic flux is created by the primary coil, which travels to the secondary coil through the transformer's core. Because we said earlier that this core is a pathway for this magnetic flux. It enhances the path of the magnetic flux. It is designed in such a way to guide and strengthen the magnetic field produced by the primary coil. And to just recall you about the experiment, when we did the experiment using a solenoid, we used an iron nail inside this solenoid. right? So when we used an iron nail inside the solenoid, we could see a very noticeable deflection, meaning the magnetic field was enhanced in that practical. So in this case also, this core quite guides, or let's say strengthen, the magnetic field produced by the primary coil. Now the flux does not need to directly touch the secondary coil. It simply moves through the core and induces voltage in the secondary coil due to electromagnetic induction. This was the answer to our first question. And second question, what can you think of the materials which will increase or decrease the efficiency of the transformer? One we already know, we are going to use that in our answer. We are using iron core. So that is a ferromagnetic material. So that is a ferromagnetic material. Okay. So about the second answer, let's see. Ferromagnetic materials are excellent at guiding the magnetic flux. So since they guide the magnetic flux, and we know it also enhances the intensity of the magnetic flux in the secondary coil, so it obviously increases the efficiency of the transformer, and also it reduces the energy losses as well. And let's think about some material which will not work so efficiently in case of transformer. So as you can see, non-ferromagnetic materials like wood, plastic, such poor conductors they do not make a very good pathway for magnetic flux. So unlike the iron core, or let's say unlike the ferromagnetic materials, these poor conductors, they do not strengthen the magnetic field as well, and which in return the transformer will be inefficient. The magnetic field would be weak, and very much more energy would be lost as heat energy. Okay. So talking about the construction, we can simply answer these questions. You can again repeat the question and try to solve it again. After the construction, let's again work in depth, or let's again study in depth about the working of our transformer. Here you can see another simpler image or simple representation of the transformer. Here you can see this is the ferromagnetic core, iron core, and this is the primary coil, this is the secondary coil as written. So now let's see how does it work. Talking about the working of transformer, it works on the principle of mutual induction, where a change in the current in one coil induces a voltage in another coil through the magnetic field. When alternating current flows through the primary coil, it creates a changing magnetic field around the coil. Again, we already saw that in our previous slides, how the AC current changes the polarity of the induced magnetic field as well. So what if there was no change in current? We are talking about AC, we are talking about the changing magnetic field. So what if the current did not change its direction? So if the current did not change its direction, obviously in the secondary coil there would be no induced EMF, right? Because if the direction of the current is not changing, the magnetic field lines are also not changing. They are constant. So if they are constant, on the other side, in the secondary coil side, they do not experience changing magnetic flux, right? So that means nothing is being generated. I mean, no EMF is being generated on the secondary coil. Okay, so that is why we are talking about AC. It flows through the primary coil, creating a changing magnetic field around the coil. This changing magnetic field passes through the core of the transformer, which helps guide the magnetic flux to the secondary coil. And of course, the changing magnetic field induces a voltage in the secondary coil due to mutual induction. Okay, so this changing magnetic field passes through the core of the transformer, which helps guide the magnetic flux to the secondary coil. And this changing magnetic field induces a voltage in the secondary coil. Now, the amount of induced voltage depends on the number of the turns in the secondary coil compared to the primary coil. So, about this working also we already talked about it earlier. This is the theoretical part for your working of a transformer. Now, let me show you a very small part of the transformer. When we were talking about the construction, I told that the iron core, they are plates of iron core laminated and they are stacked together. So the stacked iron cores, they look like this. So here you can see those single plates of irons which are laminated are stacked in this way, and they look like this. This is the core of the transformer. The primary part of this transformer is connected to the source, and the other part is connected to the rectifier to convert this AC into DC, and then further it is connected to the output. Okay, so since we are talking a lot about the number of turns in secondary coil, primary coil, we have some representations about this. The number of turns in primary coil is represented by NP. The number of turns in secondary coil is represented by NS, and the primary voltage, okay, so the AC voltage sent to the primary coil of the transformer, that is known as primary voltage or input voltage. So whatever the term arises, you can denote it with BP. And the AC voltage received from the secondary coil, or let's say the output voltage or the secondary voltage, is denoted by Vs. Okay, so far we know about the working of the transformer. We know how it is constructed, what type of materials are used in a transformer, right? So now let's try to solve some few questions. Okay, the purpose of laminating the iron core in a transformer is to A. Strengthen the magnetic field. B. Reduce eddy current losses. C. Increase electrical resistance. D. Make the transformer lighter. Okay, take some time. What is the purpose of laminating the iron core? What I said in the earlier class, what I said in the earlier time, just memorize it. Try to recall it and then solve this. Okay. So I think you were able to solve this one very easily, right? So the purpose of laminating the iron core in a transformer is to reduce eddy current losses. Let's look at the second question. What is the purpose of the insulation around the transformer windings? So I mentioned earlier that when we make the windings around the either sides of the transformer, we are using the insulator, right? We are using insulating conductors. So what might be the reason to use it? Option A, to reduce energy loss due to heat. Option B, to prevent short circuits between coils. C, to increase the strength of the magnetic field. And D, to increase the number of turns in the coil. So I think you can again easily answer this one. It's option number B, to prevent short circuits between the coils. Okay, so now let's look at this question. If the electrical supply to your home appliances becomes DC instead of AC, why would the transformer fail to alter the voltage in this situation? Okay, so when we talked about the working of the transformer, we were constantly talking that the primary coil is connected to AC source. We have used the term AC. So AC source, it generates alternating current, and we know about alternating current. It changes the direction of the current. The direction of alternating current changes periodically. So in the first half cycle, it may go in a positive direction. If we look at the sine wave of the AC, we can see, if we look at the current time graph of AC, we can see for the half cycle the movement might be in positive, and the other half cycle might be in the negative direction. Although their current is like similar, the altering phase of the current might be similar, but the direction is quite opposite. So that is for the case of AC. So let's recall about DC as well. The DC is a very unidirectional current. DC, in case of DC, the current does not alter its direction, right? So DC, the current voltage is also constant and the direction is also just one, unlike the alternating current. So we are imagining a situation, we are going to imagine a situation where in case of AC, DC is used. Again, in the working of transformer, we mentioned that when the AC source generates alternating current, it changes its direction, which again changes the polarity of the magnetic field and also the intensity of the magnetic field. That is the main reason for the change of magnetic flux on the secondary coil, which again induces the EMF in the secondary coil. So the main point here is for the transformer is the change in direction of current and the fluctuation of the current. But here let's imagine if we are going to use DC, there is no change of direction in DC, the voltage is constant, the magnetic field is constant. If the magnetic field is constant, there is no change in magnetic flux. We will just be able to measure the magnetic flux on the secondary coil, but we cannot bring any changes in the magnetic flux of the secondary coil. So what happens? If there is no change in magnetic flux of the secondary coil, no EMF will be induced, because according to electromagnetic induction, electromotive force generates when a constant magnetic flux, when there is constant variation of magnetic flux that is entering the conductor. Now let's look at this diagram. When we studied in previous class about the large sources of energy, we were constantly talking about how the our setup had transformer for the transmission of the electrical current, or let's say the voltage. So we studied about thermal nuclear plants, we studied about hydropower plant and also the wind power plant. So all three power plants, when they converted kinetic energy into electrical energy inside the generator, after the generator, our another step of connection was transformer. And in this diagram, you can see transformers of varying size. Here near the home, you can see it is quite smaller. But near the power station, let's say this, near the generation plant, you can see the transformer is quite huge. So why do you think the size of the transformer is different? Does it work differently? Do we need different type of transformers for these two separate areas, or why? I will leave you to think of a certain answer or your prediction for this question. And along with this, now let's see here, think about how electricity travels from power station to our homes. Does it need high voltage or low voltage at different points? So you could see the transformer were at different points. So does it need high or low voltage? On what factors does it depend? And how are we going to generate the required high voltage or low voltage? So we'll explore about that in the next lesson. For today, I'd like to end this class. So study well and try to solve the given questions on your own again and show it to your teacher. We shall meet in our next class.